Now, it's going to be really useful if we can make a transformation matrix whose column vectors make up a new basis, all of whose vectors are perpendicular or what's called orthogonal to each other. In this video, we're going to look at this and why this is. But first, I want to define a new operation on a matrix called the transpose. This is where we interchange all the elements of the rows and columns of the matrix. So I denote the transpose as a T, and I say that the ijth element of the transpose of A is equal to the elements on the opposite diagonal, AJI. So if I had a matrix like 1, 2, 3, 4, and I wanted to know its transpose, then I'd interchange the elements that are off the diagonal. So the 1 and the 4 stay where they are, because if I and j were the same, 1, 1, 1, 1, they would stay the same. The same for 2, 2. But the element 1, 2 interchanges with element 2, 1. So they go like that. So 1, 2, 3, 4 becomes, when I transpose it, 1, 3, 2, 4. Now, let's imagine that I have a square matrix of dimension n by n that defines a transformation with a new basis, and the columns of that transformation matrix A are some vectors A1, A2, that are the basis vectors in the new space, right? As we've said before. And I'm going to make this a special matrix where I impose the condition that these vectors are orthogonal to each other and they have unit length. That is, AI dotted with AJ is equal to 0 if I isn't equal to j. That is, they're orthogonal. And it's equal to 1 if I is equal to j. That is, they're of unit length. Now, let's think about what happens if I multiply this matrix on the left by A transpose. So A transpose is going to be given by just flipping the rows and columns of so all of the elements across the leading diagonal of A. So that is, I'm going to have A1 is going to become a row, A2 is going to become the next row, all the way down to AN, because I flip all of the elements across the leading diagonal. So when I multiply AT by A, let's see what happens. It's going to be quite magical. So if I get AT times A, then I'm going to get, well, the first element here is going to be the first row times the first column. And that's A1 times dotted with A1, and that's 1. The second element here, the first row, the second column, is A1 dotted with A2, and that's 0. And A1 dotted A3 all the way up to AN is going to give me a whole series of zeros, where this guy, remember, is AN. And then when I do the second row and the first column, I'm going to get another 0. And when I do the second row and the second column, I'm going to get a 1. Second row, third column, 0, all the way across. And when I do the third one, I'm going to get the same again. I'm going to get 0, 0. It's all going to be zeros except A3 times A3, and that's going to be that element all the way across. And what I'm gradually building up here is I'm building up the identity matrix. So what I found is that AT times A gives me the identity matrix. And what that means is that AT is a valid inverse of A, which is really kind of neat. A set of unit length basis vectors that are all perpendicular to each other are called an orthonormal basis set. Orthonormal. And the matrix composed of them is called an orthogonal matrix. One thing also to know about an orthogonal matrix is that because all the basis vectors in it are of unit length, it must scale space by a factor of 1. So the determinant of an orthogonal matrix must be either plus or minus 1. The minus 1 arises in the new basis if the new basis vector set flips space around, that is, they sort of invert it, they make it left-handed. Notice that if AT is the inverse, then I should be able to post-multiply A by AT and get the identity. That is, I can do this either way around. Which also means, by the same logic, that the rows of the orthogonal matrix are orthonormal, as well as the columns, which is kind of neat. And we saw in the last video that actually the inverse is the matrix that does the reverse transformation. So the transpose matrix of an orthonormal basis vector set is itself another orthogonal basis vector set, which is really neat. Now remember that in the last module on vectors, we said that transforming a vector to a new coordinate system was just taking the projection or dot product of that vector, so say that's the vector, with each of the basis vectors. So basis vector this one, basis vector that one, and so on, so long as those basis vectors were orthogonal to each other. If you want to pause and think about that for a moment, in the light of all we've learned about matrices, just look and think about this for a moment. Now, in data science, what we're really saying here is that wherever possible, we want to use an orthonormal basis vector set when we transform our data. That is, we want our transformation matrix to be an orthogonal matrix. That means the inverse is easy to compute. It means the transformation is reversible because it doesn't collapse space. It means that the projection is just the dot product. Lots of things are nice and pleasant and easy. If I arrange the basis vectors in the right order, then the determinant is 1, and that's an easy way to check. And if they aren't, just exchange a pair of them, and actually then they will be a determinant 1 rather than -1. So what we've done in this video is look at the transpose, and that's led us to find out about the most convenient basis vector set of all, which is the orthonormal basis vector set, which together make the orthogonal matrix whose inverse is its transpose. So that's really cool.